An incompressible fluid of uniform viscosity is in a vertical cylindrical vessel of radius r. The vessel is rotated about its own axis at an angular velocity of omega using the Navier-Stokes equation. Determine the shape of the free surface under the steady condition. So we're going to draw the vertical cylinder. Okay. So this is what it looks like. This is the flow of an incompressible fluid like water in a vertical cylindrical vessel of radius r. Next, we're going to represent this flow in our physics format, okay? So we'll say, since we are considering a rotating cylinder, the coordinate system that we're going to use is the cylindrical coordinate system. Okay, so we'll say consider a cylinder as shown in the previous figure that I just drew. Now it's showing the initial showing us the initial surface and the likely final surface. The likely final surface at steady state. At steady state. So the first analysis, physics analysis, is circumferential direction. Okay? Circumferential direction. Now, we say the velocity in the arrow direction is 0. The velocity in the z direction is 0. And the velocity in the theta direction is a function of r. The second point is, at any point in the fluid, at any point in the fluid, P or rho, P, right, will be a function of r and z. This implies that dp with respect to theta will be 0. And then the third point is, at steady state, d dt will be 0. Our fourth point As a consequence of the velocity in the theta direction equal to f function of r, our change or our dv theta with respect to theta will be 0, while our dv theta with respect to the z direction is 0. Let's remember that the coordinates are r, theta, and z for the flow. We shall analyze our different coordinates. Remember the arrow, the theta, and the z direction. So for the arrow component momentum, the momentum in the arrow direction, this is the Navier-Stokes equation, rho dv arrow dt is equal to dp the arrow plus mu the arrow 1 over arrow the arrow v arrow. Okay, plus 1 over arrow square the square v arrow the theta square minus 2 over arrow square the v theta, the theta, plus the square v arrow the z square bracket close plus rho times force. So in the arrow component, some of these terms are going to tend to 0. This will tend to 0 based on our analysis of the flow. This will tend to 0 based on our analysis. This will tend to 0 based on analysis. This will tend to 0. This will tend to 0, right? Giving us 0 equal to the p, the arrow, minus rho f arrow. So also, our f arrow, let us note this by the corner. Our f arrow formula is given by, it is also known as the body force, is given by minus v theta square all over r. It is known as the body force and also the centrifugal force. So if we substitute it into this part, what are we going to have? First of all, let's move this to the side, okay, or this to the other side. This will move to this side, okay? So it becomes this equal to this. So let's rearrange it. We'll have dp, the r, equal to rho fr. Fr is minus v, okay? So we'll say v theta square all over r. So we're going to call this our equation 1. Okay, now for our theta component of momentum. Theta component We'll still write out the Navier-Stokes equation in the theta direction, giving us rho the v theta the t equal to minus 1 over arrow dp the theta plus mu one over arrow d arrow v theta plus 1 over arrow square the square v theta all over the theta square plus 2 all over arrow square the v arrow the theta, okay, plus the square v theta all over the z square plus rho fo, okay. So this equation, some things are going to cancel out. Some things are going to cancel out. Things that are going to cancel out. Analysis of cylindrical flow. Some things are going to cancel out. Now, dv dt, t is 0. There's no t time function acting here in play, so it's a 10 to 0. Okay. Now here also, we know that the theta, with respect to theta, is tending to 0. We also know this is going to be stay put because arrow is in place already, okay? Then this one, anything that has with respect to theta will tend to 0, okay? This will also tend to 0. And anything that has dz will also tend to 0. And then f in the theta direction, no force is acting in theta direction, so this will also tend to 0. So our final equation will be 0 equal to mu d the arrow 1 over arrow d the arrow v theta. This will be our equation 2. Then finally, we're going to derive our z component momentum. Z component momentum. Okay, so first of all, write the Navier-Stokes equation in the z direction. That is dvz dt is equal to dp dz plus mu 1 over arrow d arrow dvz the arrow plus 1 over arrow square the square vz the theta plus the square vz the z square plus rho f in the z direction. F in the z direction. So this already will go to 0 because it's with respect to time. Okay, this will go to 0 because in the z direction, this is not in play. This will go to 0 because it's in theta direction. This will also go to 0. This will not go to 0 because we have our force of gravity acting there. So after applying the physics of the flow First of all, note that F2 will be G, okay? Therefore, our final equation will be 0 equal to minus dp dz minus rho G. F2 was taken as G, okay? F2 was taken as G. So if we move it over, we're going to have dp dz equal to minus rho G. This is our equation 3. So this is our equation 3.